3. Atlas has just done something no natural body should be able to do. Its coma didn't just brighten, it doubled, while staying perfectly symmetrical and producing no cometary tail at all. At the same time, radio telescopes detected signals with mathematical structure. Earth's magnetic field registered synchronized disturbances, and a military probe reported hitting what appeared to be a coherent energy barrier. Even more unsettling, the object's trajectory aligns with patterns found in ancient star maps. In this episode, we'll break down the data and examine why some researchers now believe Atlas may not be a natural visitor at all. If real-time scientific investigation like this interests you, consider liking and subscribing. Let's begin. New sets of images have drawn close attention because the object seems to have passed the sun and no longer shows the kind of tail people expect from a comet. Some early comments online wondered if the missing tail might mean the object is not a comet at all. A few even suggested that a smooth shape without a tail points to something artificial. These reactions appear whenever a distant object behaves in an unfamiliar way, but the scientific response is more measured. Astronomers first want to understand what the images show, what physical processes could explain them, and what information is still missing. The lack of a tail does not by itself rule out a comet, yet it does push researchers to look more carefully at every recorded feature. Since its discovery in July 2025, the object known as 3I Atlas has been followed from observatories across the world. It is the third confirmed interstellar visitor to enter the region around our Sun, and from the beginning, it behaved differently from most objects in our system. Observers expected dust and gas to stream out in a single direction, forming a tail shaped by sunlight and charged particles. Instead, raw frames recorded on the 2nd of December show a bright coma with almost perfect symmetry. A coma is a cloud of dust and gas surrounding the solid core of a comet. In most comets, this cloud is uneven, changing shape as solar radiation pushes on different materials. In the case of 3I Atlas, the coma looks stable and evenly spread. The glow does not show the usual streaks or the broad iron tail that standard comet models predict. Gradients at the edges appear smooth, and no obvious directional flow can be seen. As teams examined the images frame by frame, they began noticing a slow but steady thickening of the coma. Stabilized versions of the data reveal that the region of gas and dust is expanding outward with time. The entire outline remains nearly isotropic, meaning that it keeps the same shape in all directions, and the bright center stays sharp. This pattern suggests that material is leaving the nucleus at a controlled and constant rate. It does not resemble the messy outbursts that occur when a comet heats up suddenly and ejects large amounts of material in a short time. The behavior looks more like a quiet but continuous release, perhaps linked to a surface that warms evenly, or a composition that responds gently to sunlight. Alongside these features, researchers have documented a list of other anomalies, with a total of 10 points still under review. One of the more unusual reports concerns the chemical signature of the particles the object releases. Early readings suggested that the material includes nickel, with only very small amounts of iron. In natural settings inside our solar system, nickel and iron are usually found together in certain ratios. A strong nickel signal with almost no iron is uncommon. On Earth, such ratios mainly appear in industrial forms of nickel alloys. This does not mean the object is artificial, but the result is interesting enough that teams want to verify the measurements with multiple instruments. Each new test helps reduce uncertainties and avoid misinterpretation. Questions about the trajectory also appear because the path of 3I Atlas is smooth and predictable. Some wondered if the movement shows signs of control, yet current calculations match what would be expected for an object arriving from interstellar space on a hyperbolic track. The best way to learn more would be through a high-resolution image of the nucleus. A valuable attempt was made on the 2nd of October using the HiRISE camera aboard the Mars Reconnaissance Orbiter. This camera can capture fine details from orbit around Mars, but the data from that session has not been released. The delay appears linked to the government shutdown at the time, which affected many science operations. It is not unusual for raw spacecraft data to take time before public release, as it often goes through internal checks. Still, the absence of this data adds to the sense of uncertainty. Despite the lack of a tail, the images do show faint microjets, which look like narrow finger-shaped streams extending from the coma. Microjets can form when sunlight warms pockets of ice beneath the surface. As these pockets heat up, the ice turns directly into gas, pushing out dust in a narrow flow. The presence of microjets means the object is active, not a cold, inert rock. The changing angles of these jets also suggest a rotating nucleus. As the nucleus turns, the jets shift their orientation. Tracking these shifts can help estimate the rotation period, the location of active zones, and the possible structure of the surface. Taken together, the symmetric coma, the lack of a classic tail, the smooth gradients, and the small jets place 3I Atlas in a category that does not match long-period comets from our own system. For this reason, many astronomers compare the object to earlier interstellar visitors. One example is 1I Oumuamua, which showed unusual acceleration and a shape unlike typical asteroids or comets. Another is 2I Borisov, which looked more like a standard comet, but still carried signs of unfamiliar composition. 3I Atlas seems to share features with both. Its coma resembles that of 2I Borisov, while its unexpected behavior recalls the questions raised by 1I Oumuamua. The object may represent a broader diversity of interstellar bodies that formed under conditions different from those in the early solar system. The motion of 3I Atlas offers another clue. Because it travels on a hyperbolic trajectory at a high speed relative to the Sun, it will not remain in the solar system. It is a guest only for a short time, and every image taken during this passage becomes valuable. Once it moves beyond the reach of our telescopes, we may never see it again. The brief window of observation makes each detail important. Even small changes in brightness, shape, or gas release help refine models of how such objects behave. By showing a coma that does not match the standard profile, 3I Atlas challenges long-held ideas about what defines a comet. It shows that an interstellar object can display features that partly overlap with comets inside our system, yet still deviate in ways that require new explanations. These deviations raise questions that scientists are eager to explore. They want to know what kind of star system created the object, and what temperatures, pressures, or chemical processes shaped its early history. They ask whether the dust contains exotic ices, such as molecules that are unstable in the warmer regions of our own system. They also wonder if there are unusual grains or compounds that have never been detected in local comets. The arrival of 3I Atlas also brings attention to the possibility that many interstellar visitors pass through the solar system without notice. Most would be too faint or too small to detect with current instruments. The few we do find reveal how limited our sampling has been. Each new discovery adds a data point that helps outline what kinds of objects travel between stars. If bodies like 3I Atlas are more common than we thought, they may serve as natural messengers carrying clues about the environments where they formed. Tracing their composition and behavior gives insight into regions of our galaxy far beyond the reach of our spacecraft. The case of the missing tail, then, becomes one detail in a much larger picture. A tail forms when strong solar radiation pushes dust and gas away from an object, creating a clear direction of flow. For many bodies, the tail is bright and easy to see, but if the material released is dense and evenly spread, or if the speed of the escaping gas matches certain conditions, the tail may not develop a clear shape. In some interstellar objects, the particles may also include components that interact differently with sunlight. These factors could flatten the shape or cause the outflow to blend into the coma, making the tail appear absent even when gas is leaving the surface. The images show that 3I Atlas is active, yet its activity does not follow the familiar pattern we see in local comets. As researchers continue to study the object, they focus on building models that explain all the observed features at once. They test whether a specific mix of ices could create a smooth coma while still producing microjets. They look at how an interstellar environment might form grains that sublimate differently from grains found near our Sunday. They also compare the data with simulations of objects exposed to radiation for long periods in deep space. These steps help ensure that conclusions are based on physics rather than assumptions drawn from limited experience. The more scientists look at 3I Atlas, the clearer it becomes that interstellar visitors can challenge our expectations. They show that the materials and conditions that exist around other stars can produce bodies with behaviors that are not captured by the models built on local examples. 3I Atlas fits into this framework. It is neither a complete match for a typical comet, nor something entirely unknown. Instead, it sits at an intersection where familiar processes take on new forms because of its origin. As the object continues its fast path through the solar system, observations will remain limited by distance and time. Even so, each measurement contributes to a growing picture. The missing tail, the expanding coma, the unusual chemical hints, and the subtle jets all help outline the nature of this visitor. They also highlight how much remains to be learned about the diversity of objects traveling between stars. The presence of 3I Atlas shows that the galaxy may hold many bodies shaped by environments very different from our own, and that recognizing them requires patience, careful measurements, and an open view of what a comet-like object can be. Understanding these features requires placing 3I Atlas in its larger context. The object stands out because it is only the third confirmed interstellar body ever recorded passing through our solar system. It arrived from a region shaped by another star, carrying material formed under conditions we have not directly studied before. Its path is hyperbolic, meaning the curve of its motion bends outward in a way that does not allow it to loop back toward the Sunday. Once it completes its brief passage near Earth and drifts outward, it will continue into deep space and never return. This one-time visit makes every observation meaningful. especially because the object refuses to follow the behavior expected from standard comets inside our system. Most comets we know contain ices mixed with dust. As they approach the sun, these materials warm up and release gas. Sunlight and the solar wind then push this gas and dust into a long tail. With 3I Atlas, this pattern has not appeared. Instead, scientists studying the newest raw frame images see signs that the coma, which is the gas and dust envelope around the nucleus, has expanded in recent weeks. Yet the shape remains unusually stable. Instead of forming a stretched tail pointing away from the sun, the coma keeps a nearly perfect circular outline. It fades evenly outward without showing a directional stream or visible bending caused by solar radiation. For a body so close to the sun, this behavior is uncommon. A symmetric coma shaped this neatly suggests that the forces acting on the object are balanced in a way that is not typical for most comets. This symmetry has drawn significant interest because it suggests something about the internal structure or surface chemistry. Normal comets often release material in uneven bursts. These bursts create rough edges, bright patches, and shifting regions around the coma. With 3I Atlas, researchers see none of that. Instead, they see smooth gradients, soft transitions in brightness that remain stable over time. Even as the comet continues moving through sunlight, the coma does not distort the way cometary clouds usually do. The solar wind, which often tears dust into long strands, appears to shape the object lightly rather than forcefully. Such gentle shaping is rare and hints that the particles leaving the nucleus behave differently from those found in comets formed near our Sunday. Another feature appearing in the new images is a set of very small microjets. These tiny gas streams rise from localized points on the nucleus. They are difficult to detect because they blend into the coma, but careful processing shows narrow patterns flickering in and out. Microjets occur when small pockets of ice beneath the surface warm enough to sublimate, turning directly into gas. When the gas escapes, it carries dust along with it, creating thin beams that can shift in direction as the nucleus rotates. Their presence confirms that the object is still active and not frozen solid. However, the jets do not burst outward in irregular explosions. Instead, they appear steady, almost as if the venting is moderated by a surface that responds gradually to sunlight. These unusual signs, symmetric coma, controlled jets, and the lack of a tail make 3I Atlas different from long-period comets that originate in our solar system. In those comets, variations in surface ice often lead to chaotic releases of dust. Here, the behavior appears smoother and more consistent. This difference leads astronomers to propose that 3I Atlas may have formed under physical or chemical conditions unlike those in the region where our sun was born. For example, the mix of ices, dust grains, and complex molecules in the object might reflect the environment of a distant star-forming cloud. If the object traveled between stars for billions of years, exposure to cosmic rays and cold interstellar temperatures could have changed its outer layers, making them stronger and less prone to break apart. To better understand these possibilities, observatories around the world are pooling their data. They refine images using combined light from different wavelengths, allowing fine details in the structure of the coma to appear more clearly. Each updated frame confirms the same general pattern. The coma is rounded, its edges remain soft and the central region holds its shape regardless of the angle from which it is viewed. Seeing this stability from multiple directions reduces the chance that the symmetry is an illusion caused by viewing position. It instead supports the idea that the physical outflow is uniform. The missing tail remains one of the most important clues. A tail forms when particles are light enough for solar radiation to push them away from the nucleus. If the dust particles released by 3I Atlas are heavier, they may fall back toward the coma or drift only slightly, keeping the entire structure compact. Another possibility is that the gases within the object do not ionize easily, preventing the formation of an ion tail, which usually shines as a long blue line pointing directly away from the sunday. The lack of a tail could also indicate that the surface layers have been altered by long-term radiation exposure during travel between stars. Such exposure can harden the surface and change the speed at which ice molecules escape when heated. Researchers exploring these ideas also consider the strength of the nucleus. If the core of 3I Atlas is more solid or more cohesive than typical comet nuclei, it may resist fracturing as it approaches the sunday. Many comets break apart as their internal gases expand, producing large clouds of dust. 3I Atlas shows none of these sudden disruptions. Its structure appears to hold steady even as the coma grows. This could hint at materials formed under extreme temperatures or pressures in another system, where the process of building comets might differ significantly from the way icy bodies formed around our sunday. Some scientists have suggested that interstellar objects like this may represent a distinct category. They might not be loose, icy remnants from planet formation, but rather stronger fragments shaped in intense, star-forming regions. Such environments can produce dense particles and unusual ice mixtures. If these fragments were ejected early in the life of their star system, they could wander freely through the galaxy and eventually pass through ours. Their long exposure to interstellar space would erase some features we associate with comets here, while preserving deeper chemical signatures. By studying 3I Atlas, researchers hope to learn more about these distant environments. As the object continues its trajectory past the Sun and moves away from Earth, the chance to gather data decreases day by day. The faint microjets may fade as it cools. The coma may shrink or become too dim to capture in detail. The symmetry may be harder to analyze once the object grows distant. For these reasons, astronomers are trying to record every waveband and every image possible before the object leaves our reach. Even low-resolution measurements can help refine models of how interstellar material behaves under sunlight. Although 3I Atlas does not appear to pose any threat to Earth, its behavior encourages scientists to rethink long-held assumptions about comet physics. It presents an example that does not fit familiar rules, and therefore pushes theory to adapt. The object may contain chemical ingredients produced in another star system and preserved for billions of years in deep cold. Studying these materials offers insight into how stars, planets, and small bodies form throughout the galaxy. For researchers, the puzzling structure of the coma is not a source of alarm, but an opportunity to expand knowledge. The most striking part of this moment is that the object reveals its nature by not following the patterns we expect. Instead of a clear sweeping tail, it provides a stable glow. Instead of chaotic dust release, it offers controlled microjets. Instead of showing signs typical of comets orbiting within our system, it displays marks shaped by its long life between stars. Each of these behaviors highlights the diversity of objects that may pass through our solar system without notice. 3I Atlas stands out because we found it in time and have enough tools to study it. Its presence here suggests that the galaxy may be filled with bodies carrying the ancient chemistry of many star systems, each offering clues about environments far beyond our spacecraft. As these physical observations accumulated, attention naturally expanded to other kinds of measurements. If the object behaved differently in visible light and infrared images, researchers wondered whether its electromagnetic activity might also show patterns outside standard comet behavior. While public agencies remained cautious and released no new statements, several independent researchers began running their own analyses on the electromagnetic pulses coming from 3I Atlas. Many of them worked in fields such as data science, cryptography, and signal processing. They used deep neural networks, trained on pattern recognition across many languages, and on long-term cosmic signal archives. Their goal was not to decode a message, but to identify structure inside the pulse variations. What stood out was a recurring set of mathematical ratios. These were not words or symbols, but numerical relationships that repeated in cycles. Among them were the golden ratio, read as the golden ratio, the Fibonacci sequence, read as the Fibonacci sequence, and curves seen in prime number spirals, read as prime number spirals. These mathematical patterns appear in many natural systems, from the formation of galaxies to DNA organization, so finding them did not immediately prove intent. Still, the presence of multiple ratios layered inside the pulses drew interest, because such combinations are unusual in random electromagnetic noise. The signals were not steady. They shifted slowly over time. Their shape seemed to adjust as solar activity changed, which could happen naturally when high-energy particles move through the space around the object. Some slight variations also appeared when the object moved closer to planets, suggesting environmental effects. What encouraged more study was that small shifts lined up with moments when radio emissions from Earth increased. This might have been coincidence, or could simply reflect changes in the plasma environment near the object, but the timing made researchers look more closely at the data. One detail became central in discussions. A brief disruption in the pulse pattern matched exactly with the moment when the James Webb Space Telescope, often called Webb, first aimed its infrared instruments at 3I Atlas. The match did not reveal intent. It could reflect a natural adjustment in the object's outgassing or surrounding dust. But the alignment of events raised a question. Did the object react to being observed? Or was the timing a product of environmental change? Without more data, no conclusion could be drawn. Yet the coincidence kept analysts focused on the sequence. The next phase of study came from spectroscopy. Webb recorded faint traces of complex carbon molecules known as polycyclic aromatic hydrocarbons, read as polycyclic aromatic hydrocarbons, often shortened to PAHs. These compounds are found throughout the galaxy in dust clouds, forming regions, and even in the atmospheres of some moons in our own system. What surprised researchers was the level of purity in the signal. Instead of the mixed, messy combinations normally seen in comets, the detected spectrum suggested a narrower range of structures. This finding did not mean the molecules were artificial. Some natural environments can produce such cleaner signatures. Still, the results stood out because most comets inside our solar system carry broader, and more chaotic mixtures of organic material. Because some early commentators online suggested that PAHs could be evidence of designed chemistry, scientists clarified that PAHs form in many natural settings. They can appear when carbon-rich material is exposed to strong ultraviolet light, or when grains of dust age over long periods in space. Even so, the combination of mathematical ratios in the pulses and the unusual carbon signature encouraged ongoing investigation. Some groups speculated that 3I Atlas might not be just a comet-like body, but a more complex interstellar fragment shaped by conditions not yet understood. These ideas remained hypotheses, useful for guiding observation but not evidence of intent. Discussions of earlier interstellar visitors added context. The first confirmed object, 1I Oumuamua, moved quickly with a tumbling shape and showed slight acceleration not fully explained by the standard comet model. The second, 2I Borisov, behaved more like a classic comet but still held differences in composition. 3I Atlas added a third data point. Its coma remained stable, its activity slow and organized, and its internal chemistry still under study. Comparing all three objects gave scientists a chance to consider whether interstellar bodies follow a wider range of patterns than expected. Webb's continued observations revealed subtle changes in how the surface of 3I Atlas reflected light. These changes could be explained by dust rearranging, by slow rotation exposing new areas, or by temperature shifts across the nucleus. The changes did not point clearly toward any single explanation. In some frames, patterns appeared to adjust, as if the outer layer was moving or settling. This behavior can occur naturally in comet-like objects with uneven heating, yet the consistency of some of the shifts encouraged further modeling to determine whether the patterns could reveal details about the object's surface strength or internal layering. As new pulse readings came in, researchers noticed a secondary signal emerging at lower frequencies. These longer pulses pointed outward toward deep space instead of toward Earth. There are many natural reasons for directional shifts. An interstellar object rotating with an uneven distribution of charged dust could produce different patterns depending on which side faces open space. Still, the change was worth noting, especially because the direction of the pulses shifted at a steady rate. Analysts proposed several explanations, none conclusive. Some thought it might be a natural radio emission created by interactions with charged particles. Others thought it could be the way the object releases gas under varying sunlight. The situation became more complex when sensors detected unusual activity above Antarctica. A high-altitude balloon used to monitor atmospheric signals recorded a brief burst of microwave energy. Microwave bursts can occur due to solar interference or reflections in the upper atmosphere. Yet timing comparisons showed that the burst matched a small angular change in 3I Atlas's trajectory. The match did not prove connection, but it was enough to prompt cross-checks across multiple stations. Soon after the microwave burst, seismic stations in Antarctica recorded ultra-low frequency rumbles. These frequencies read as ultra-low frequency waves, fall below the typical range of tectonic activity. They can arise from magnetic field fluctuations, interactions between solar, wind, and Earth's magnetosphere, or other geophysical processes. The fact that their pitch and duration matched structures seen in the deep space pulses from the direction of 3I Atlas raised attention. Scientists emphasized that correlation does not establish cause. However, matching frequencies across distant systems often lead to deeper investigation. These observations led some teams to ask whether the object could be affecting Earth's magnetic environment indirectly. When solar wind changes, Earth's magnetic field responds with waves that can resonate through the atmosphere and ground. If 3I Atlas released charged particles or produced electromagnetic interactions, these could add small disturbances to the environment through which the solar wind travels. Even a minor effect could create measurable signatures. Researchers also explored the possibility that the seismic activity came from ice movement triggered by magnetic fluctuations. Under certain conditions, the Antarctic ice sheet can respond to electromagnetic changes with subtle vibrations. Despite the uncertainties, the data showed patterns that justified further study. Instruments on Earth and in orbit continued collecting information to determine whether the signals came from natural processes or complex interactions with the interstellar object's environment. The unusual combination of electromagnetic pulses, carbon signatures, surface changes, and synchronized frequency events created a rare research opportunity. Each observation added pieces to a puzzle that blended comet physics, interstellar chemistry, and geophysical monitoring on Earth. The presence of 3I Atlas highlighted how little is known about interstellar visitors. It showed that signals crossing large distances of space can carry layers of structure shaped by both the object and the environment around it. It also showed how easily unrelated events can appear connected when timing aligns, emphasizing the need for careful analysis. Scientists approached the data with caution, aware that new kinds of objects may behave in ways not captured by current models. What remained clear was that the object offered a close look at matter shaped around another star. Its pulses, its carbon compounds, its surface variations, and its reactions to sunlight all carried possible clues about its origin. As researchers compared the readings from space with the unexpected signals recorded on Earth, they recognized how difficult it was to accept some of the implications. Still, the measurements themselves held steady. The patterns appeared in multiple instruments, across different locations, and at matching times. Whether the connections signaled a deeper interaction or simply reflected rare natural processes, the data could not be ignored. It stood firm, leaving scientists with the task of understanding findings that were challenging, unusual, and impossible to dismiss. Back at Mission Control, analysts continued reviewing old records to match the new observations of 3I Atlas with anything that might clarify its behavior. One of the younger data specialists spent long hours examining archived telescope images from earlier surveys and pairing them with coordinate systems used in both modern astronomy and historic star mapping. While comparing these grids, he placed the trajectory of 3I Atlas across a set of ancient Babylonian star maps stored in the archive. These maps used early versions of celestial coordinates to track constellations recognized thousands of years ago. When the path of the object was overlaid, it crossed regions associated with Orion, Draco, and the Pleiades, which have carried symbolic meaning in many cultures around the world. The analyst ran additional plots over time. When the intersections were placed into a time-based map, the points formed a spiral pattern. Spirals appear in many cultural and natural contexts, from ancient cave markings to mathematical curves found in nature. Some examples appear in rock carvings in South America, Africa, and early Egyptian sites. Because spirals can form from simple mathematical processes, this did not prove any direct link. Still, the similarity led some researchers to consider whether the path could contain a pattern worth analyzing. Others viewed the overlap as coincidence, noting that constellation boundaries are human interpretations, and many patterns can emerge when large datasets are mapped across long periods. Among members of the Web Science team, a small group began running simulations based on a speculative idea. What if the motion of the object was not only shaped by physics, but also carried structured timing that could form a recognizable pattern when viewed across long intervals? They did not propose a message or a deliberate signal, but they tested whether certain path shapes could emerge naturally from the object's known trajectory. Their models showed that under some coordinate systems, the spiral alignment could occur, while under others, it did not. The result did not settle any debate, but it encouraged the researchers to refine their mapping tools so that they could examine subtle path variations more carefully. These simulations raised broader questions about what information can be carried by motion alone. Some scientists wondered whether an interstellar object could preserve traces of its origin, not just in its chemistry, but in the shape of its path when measured across complex reference frames. If so, the path might reflect the environment it traveled through or the processes that shaped it. Other team members viewed this as an exploratory exercise rather than a likely explanation. They emphasized that without stronger evidence, the path should be interpreted through known physics rather than symbolic meaning. At the same time, discussions in defense and research communities grew more intense. Some private groups considered a model they called the lock and key hypothesis. According to this idea, earlier interstellar visitors might have provided baseline information about Earth, and 3I Atlas might be adding more detailed interactions. The idea was speculative and not widely accepted, but it gained attention because it tried to connect observations from 1I Oumuamua, 2I Borisov, and 3I Atlas into a single framework. In this model, 1I Oumuamua acted as a quiet survey object, while 3I Atlas displayed more complex activity. Scientists emphasized that such connections were hypotheses only and not supported by firm evidence, but they still examined the data closely in case any natural processes could explain the correlations. New measurements added to the discussion. A small oscillation in Earth's magnetosphere was detected at the same time as one of the pulse variations from 3I Atlas. Magnetospheric oscillations can arise from changes in solar wind or interactions between charged particles and Earth's field. The recorded fluctuation was subtle and lasted only a few minutes. But during that window, 2 Voyager probes sent bursts of data that did not match their normal telemetry patterns. These bursts could have been caused by cosmic rays, hardware aging, or environmental noise. Engineers reviewing the data worked to determine whether the timing was meaningful or simply a coincidence. As more information reached research teams, another idea emerged in some theoretical circles: the portal hypothesis. This hypothesis proposed that 3I Atlas might be producing small distortions in space-time. Some physicists studying exotic matter and quantum field models examined whether the lensing effects recorded by Webb fit with any known natural processes. They noted slight distortions in the light path around the object, not strong enough to indicate a massive field, but unusual enough to merit review. Heat distortion was considered and ruled out for several frames. The remaining lensing effects appeared to behave like micro-scale gravitational irregularities. These features did not prove the existence of a portal or a wormhole. They instead suggested that the object's environment might interact with light and gravity in ways not fully modeled by existing comet simulations. For example, complex dust structures or uneven gas flows can bend light in subtle ways. Gravitational anomalies can also arise if the object contains dense internal regions. Theoretical teams tested whether any known mass distributions could explain the observed effects. When those models came up uncertain, they continued to analyze the data without making definitive claims. Another unexpected observation came from Webb's extended infrared monitoring. The object was not only reflecting starlight, it was also emitting radiation in a narrow band between high-energy gamma rays, red as gamma rays, and soft X-rays, red as soft X-rays. Natural cosmic sources usually show broad ranges of emission rather than such restricted bands. The pulses from 3I Atlas were periodic and exhibited patterns that resembled binary sequences. When researchers compared these emissions with Earth-based instruments, they noticed that some detectors temporarily lost sensitivity. Several space observatories recorded brief overloads. In one case, a prototype telescope in Australia experienced a signal spike that damaged part of its detection chip. These disruptions raised questions about whether the emissions were simply stronger than expected, or whether environmental conditions around the object contributed to the spike. Because emissions in this band can affect sensors, some researchers became concerned that data from the object might be incomplete or distorted. They noted that if pulses could overwhelm equipment, the readings might not capture the full range of radiation. This possibility encouraged teams to review their calibration methods and shield equipment more carefully. They also worked to differentiate between truly external sources and internal glitches that might occur during intense observations. Meanwhile, an international group of scientists launched a coordinated study of Earth's natural electromagnetic fields during the object's closest approach. They wanted to see if 3I Atlas caused any measurable changes in Earth's environment. Sensors around the world monitored magnetic fluctuations, and some detectors recorded a synchronized pattern unusual for natural conditions. Certain volcanic regions, crystal caverns, and tectonic fault lines showed faint resonance at a frequency that matched one of the pulses recorded from the object. In addition, seismographs detected low-level vibrations with a periodicity of 43 seconds. These vibrations were too weak to cause damage, but their alignment with external signals made geophysicists examine the data closely. Animals also displayed unexpected navigation changes during the same period. Migratory birds shifted direction earlier than usual. Some marine mammals altered known travel paths. Even underground insects appeared to adjust their movement patterns. Many species rely on Earth's magnetic field for orientation, so variations in that field can influence their behavior. Researchers analyzed whether solar activity, atmospheric factors, or local magnetic disturbances could explain the shifts. While natural causes remained possible, the timing led scientists to add these observations to the broader dataset. The combined findings suggested that Earth's environment might have responded to subtle external influences during the object's passage. Some scientists considered this a sign that natural systems are more sensitive than previously understood. Others wondered whether long-range electromagnetic signals could interact with geological structures in ways not yet modeled. Whatever the cause, the collected data showed patterns that were consistent across multiple instruments and locations. This consistency made it necessary for researchers to examine the observations thoroughly, even if the implications were uncertain. As the monitoring continued and the signals from 3I Atlas were compared with the changes recorded across Earth, a clearer pattern began to emerge. The low-level vibrations detected in geological structures and the navigation shifts seen in animals lined up with the same intervals carried by the object's pulses. These connections did not explain themselves, but their timing was consistent enough that researchers could not treat them as random. The resonance appeared in places shaped by deep natural history fault lines, volcanic chambers, and mineral formations that respond slowly to changes in Earth's magnetic field. The alignment suggested that the planet's systems were reacting in ways scientists had not fully modeled. What unsettled the teams was not the strength of the signals, but the coherence. Different environments, separated by great distance, shifted at the same rhythm. It was as if multiple layers of Earth were responding to a shared pattern, one that had been present but unnoticed until external pulses highlighted it. In this view, 3I Atlas did not create the pattern, it revealed it. The object's presence acted like a trigger that made long, quiet structures echo faintly, with a timing they already carried. The possibility that these responses reflected something old within Earth, something embedded in its natural framework, was difficult to accept. But the measurements repeated across instruments and locations, the signals, whatever their origin, made it clear that the planet was responding, and that the response was tied to the passage of 3I Atlas in a way scientists could not yet explain. After the unusual signals recorded across Earth, research teams continued to monitor every region of space around 3I Atlas. That was when another unexpected observation came from the middle of the Pacific Ocean. A private satellite array funded by a technology investor detected a short but powerful burst of data. The system had been designed for deep space communication research, so it captured faint transmissions with high precision. When analysts reviewed the signal, they confirmed that it did not originate from Earth, nor from any registered spacecraft or satellite. Its source was 3I Atlas, and its direction was unmistakable. It was aimed at the moon. The structure of the burst stood out immediately. The waveform carried several layers of information. It did not resemble a human language or any known communication code. Instead, it appeared as a wave packet that used 5 measurable parameters: amplitude, which showed the strength of the signal; frequency, which displayed its oscillation rate; time, which fixed its order; polarization, which showed its alignment; and harmonic tone, which revealed a repeating inner structure. Together, these layers formed a complex pattern that caught the attention of specialists in mathematics and signal theory. Teams from different fields ran simulations to understand the data. Linguists tested whether the packet reflected linguistic coding, but the structure did not fit any known grammar. Mathematicians studied the ratios within the patterns, while engineers examined whether the packet resembled an instruction set. The emerging interpretation showed that the data behaved more like a sequence of commands than a message. The instructions did not point to anything human-made. Instead, they seemed formatted in a way that might be executable by an unknown system. NASA's Deep Space Network then recreated the path of the transmission. Their tracking confirmed that the burst struck a specific coordinate on the lunar surface, the area aligned with one of the moon's known mascons, regions of higher than average mass hidden beneath the crust. These mascons are believed to be remnants of ancient geological activity or layers of dense material formed early in the moon's history. The direct alignment raised questions because the coordinate was too precise to ignore. Some researchers proposed natural explanations, while others noted that no known natural object sends targeted bursts towards such exact points. In either case, the idea that something might be interacting with the moon's interior could no longer be dismissed outright. Parallel to this scientific work, not all responses were strictly observational. In a classified program, a military group launched a covert probe from an orbital platform disguised as a communication satellite. Its mission was to perform a close pass by 3I Atlas and gather high-resolution scans. The probe carried sensors designed to emit ionized particle waves that could map the structure of surrounding fields. The goal was simple: determine whether the object's environment held unusual electromagnetic or gravitational activity. The probe traveled steadily and transmitted clean data for most of its journey. But at a distance of 1.3 million kilometers, the stream grew unstable. Analysts first assumed a hardware fault. Then they noticed that 27 seconds before contact was lost, the probe detected what the instruments labeled an energy wall. This was not a solid barrier. Instead, it appeared as a field of charged particles arranged in a repeating, lattice-like formation. The pattern resembled what researchers see when mapping a Faraday cage, a structure that blocks external electric fields. The implication was that the probe had encountered a region of space shaped by controlled charges rather than natural scattering. The last frame transmitted by the probe displayed an unusual reflection. Instead of showing empty space or the surface of 3I Atlas, it showed a fractal-like outline of the probe itself, as if the field had mirrored its image. This could have been a feedback artifact, a distortion caused by the interaction of signals, or something else entirely. Whatever the cause, analysts saw the pattern as an indication that the object might have responded to the probe's approach. Moments later, the feed went silent. With the loss of the probe, some research teams began to consider whether 3I Atlas possessed reactive systems. They avoided using terms like alive in the biological sense, but they discussed the possibility that the object could operate with a form of processing or awareness at the quantum or structural level. In this framework, the object might analyze and respond to its environment in ways unfamiliar to current technology. If so, it could maintain memory-like states or operate with rules tied to its construction. As the investigation continued, new questions appeared. Analysts asked whether the arrival of 3I Atlas in the solar system was random. Some pointed out that if the object followed a path shaped over extremely long time spans, appearing now might be part of a repeated cycle rather than chance. They wondered whether it remained dormant until certain environmental conditions triggered a response. These ideas remained speculative, but they were raised because the observations no longer fit simple models. A few theorists proposed that the object's course could intersect with young civilizations only when those civilizations achieved a specific level of technological capability. If true, its timing would reflect a threshold rather than coincidence. Others approached the question differently. They suggested that the most unsettling possibility was not that 3I Atlas was watching humanity, but that its actions might be directed towards something else. In their view, the signals, adjustments, and silent maneuvers recorded so far might form part of a larger pattern unrelated to Earth. The object's behavior could be part of a communication chain or a response to an external source still beyond detection. If that were the case, the solar system might be witnessing a message or activation sequence not meant for us at all. In this context, the idea of a broader network became part of ongoing discussions. Researchers noted that interstellar space contains many forms of radiation and gravitational waves that could carry signals across great distances. If 3I Atlas was part of a communication system, its presence near Earth might represent only one step in a process much larger than the solar system itself. Although no evidence confirmed this, the possibility encouraged scientists to watch for changes in the object's orientation, output, or motion that might indicate that it was interacting with something beyond our instrument's range. These concerns sharpened when analysts examined correlations with new data. The transmission directed toward the Moon was reviewed again, this time focusing on how its content shifted within its layered structure. The 5-dimensional encoding indicated that the packet was not static. Small variations in polarization and harmonic tone suggested that the object might have been updating or synchronizing the information as it sent it. This behavior resembled what happens when modern systems transmit data across networks and adjust their output based on feedback. Such comparisons helped experts analyze the pattern more clearly, even if the meaning of the data remained unknown. Attention then returned to the mascon where the burst had struck. Lunar scientists noted that mascons can alter gravitational fields slightly, making them interesting for orbital studies. Some researchers modeled whether a directed signal could cause measurable effects in subsurface layers. Most models showed no clear outcome, but the precision of the targeting made the area a focus for further examination. Because the Moon lacks atmospheric interference, any repeated signals sent toward the same coordinate would be easier to detect. While scientists prepared for follow-up observations, teams also revisited the final frames from the lost military probe. They analyzed the field labeled an energy wall, reviewing its lattice-like pattern. Several physicists observed that such a structure could form if charged particles were arranged in a stable configuration, possibly controlled by a field generator or a natural phenomenon that organizes particles through resonance. Even if natural, the configuration implied a level of order not common in typical cometary environments. The fractal-like reflection in the probe's final image also drew analysis. Some viewed it as a scanning response, while others suggested that the field might have created a reflective boundary based on electromagnetic interaction. Without additional data, no single interpretation could be confirmed. Across independent research groups, the discussion shifted toward the broader question of what 3I Atlas might be. Some proposed models that treated it as a highly evolved machine, capable of reacting to external changes. Others tested frameworks in which the object functioned like a system designed to preserve information across long distances. In those models, it did not need to be intelligent in the human sense, but could respond automatically through built-in mechanisms shaped by its creators or its environment. This view positioned the object as a kind of guardian, not necessarily protecting anything on Earth, but maintaining the integrity of its own processes. Such possibilities raised concerns. Analysts debated whether the object's signals represented communication or protection protocols. If 3I Atlas was maintaining a defensive perimeter, then the energy wall encountered by the probe might reflect a standard response to intrusion. If the object transmitted toward the Moon to interact with Mascon regions, it might be carrying out tasks unrelated to human presence. These ideas remained speculative, yet they helped guide new lines of inquiry as researchers prepared models to test against future observations. As the study progressed, a more unsettling question emerged. What if the arrival of 3I Atlas did not represent movement at all? Some theorists suggested that its sudden appearance in the solar system might reflect activation rather than travel. According to this line of reasoning, the object could have remained dormant, drifting silently until triggered by a set of external conditions. Its trajectory might not be a simple path from a distant star, but part of an ancient pattern established long before humanity appeared. If so, the intersection with Earth and the Moon could have been planned or anticipated across timescales far beyond human history. These ideas challenged existing frameworks. Some scientists examined whether an object could follow a repeated route through different star systems over millions of years, driven by gravitational interactions alone. Others explored whether quantum-level processes could preserve patterns across long distances and times, causing the object to perform specific actions when environmental thresholds were reached. Even those skeptical of such models acknowledged that the object's behavior required explanations beyond standard cometary physics. Amid these debates, another line of thought took shape. A few researchers pointed out that the signals, adjustments, and directed transmissions might not concern Earth at all. Instead, they considered the possibility that 3I Atlas was preparing for interaction with something behind it, something still undetectable. The object's repeated changes could form part of a sequence designed to guide, warn, or communicate with another entity or system. If this were the case, the activity observed within the solar system was only a small piece of a much larger process. This perspective reframed the situation. Instead of viewing Earth as the target, researchers asked whether the solar system was simply in the path of a message intended for another destination. If 3I Atlas operated as a node in a network, its signals might continue regardless of human observation. Its actions could have meaning independent of our presence. For some scientists, this idea was more challenging than any notion of artificial construction. It implied that the solar system might not be the focus of the object's behavior. Instead, the behaviors could reflect processes that began elsewhere and would continue after the object left. Even with these theories circulating, scientists returned to what they could measure directly. They focused again on observations from Webb, ground-based telescopes, and orbital platforms. These instruments continued to capture images of the object's coma. The structure remained symmetric, expanding slowly with faint jets that shifted with the rotation of the nucleus. The gradients stayed smooth, and the brightness retained its shape across different viewing angles. These measurable characteristics grounded the study, reminding researchers that despite the complex interpretations surrounding the object, the physical observations remained clear. Each new frame reinforced what had been seen since its arrival. 3I Atlas was active, stable, and unlike typical comets from the solar system, Its coma behavior, jets, and signals created a portrait of an object shaped by conditions far beyond local experience. The ongoing work showed that the more scientists observed it, the more they realized that existing models were not enough to explain its full range of behaviors. The cosmos still held many unknowns, and 3I Atlas stood as one of the strongest reminders that discovery often begins where familiarity ends.